Welcome to the Deep Dive, your shortcut to understanding, well, the complex systems that run our world.
Hmm.
Today, we are stripping down the foundations of science and engineering, going right back to basics.
That's right. We're looking at a whole stack of fundamental source materials here, lectures, tutorials, the works, covering the basic mathematical rules that everything else is built on.
Yeah, and our mission really is to quickly get a handle on this underlying language of science. We'll cover core concepts from, well, arithmetic consistency stuff we think we know right up through exponential growth,
It's
logarithms.
about understanding that journey, isn't it?
Yeah,
From something simple like AB plus C all the way to, say, Euler's constant at
like
E
it's just
day.
tracing that path from fixed rules to the dynamics of the real world. Okay, let's unpack this.
It's a really crucial deep dive, this one, because, like you said, we go from the absolute certainty of distributing terms in algebra, which is just fundamental for system reliability,
Mhm.
all the way to the C and all.
Yeah.
Which, that's the language of continuous change, of growth and decay.
Yeah.
These basic ideas, they're the bedrock for every single complex calculation that engineers and scientists do later on.
Okay, so let's start right at the beginning. The cornerstone, the distributive rule.
Right.
Conceptually, it just says when you multiply something by a sum, you hit every term inside that sum with the multiplication. 80 plus C equals AB plus AC.
Yeah, and it feels intuitive, maybe, if you think about geometry. Like
Yeah.
the total area of a big rectangle has to be the sum of the smaller rectangles inside it,
Yeah.
right? AB plus AC.
Sure, that makes sense visually.
But the source material, it really hammers home a critical point. This rule must hold true for all numbers, and that includes negative numbers. That's the key test.
Exactly. The sources spend time actually proving this, showing the math works even with negative signs involved. Now, some might ask, why bother? Isn't confirming this kind of arithmetic consistency a bit overkill?
Well, no, not at all. Because think about it. If those foundational rules started breaking down at the simplest level, say if multiplying two negatives didn't consistently give a positive life, then the whole mathematical system loses its integrity.
Ah, okay.
And for engineers building bridges or circuits, that consistency, it's just non-negotiable. You absolutely have to trust that the math works everywhere, across the board. No exceptions.
And the materials had that really good financial example, didn't they, to show the consistency?
Yeah, the friend losing a day of work.
Right. So losing a day is like -1. And you multiply that loss across their income, which is positive, and their travel cost, which is also a cost, so negative.
Exactly. And that negative travel cost
Yeah.
multiplied by the negative day lost,
Yeah.
it becomes a positive credit. It reduces the total loss.
So -1 times, say, 100 minus 5 equals -100 plus 5, a net loss of 95.
Perfect. It confirms the rule works exactly as expected, even with negatives mixing in. It shows the integrity holds.
Okay, got it. Now, shifting gears slightly to fractions. The rules here seem focused on, well, efficiency and clarity.
Pretty much. For multiplication, it's straightforward, isn't it? Multiply the tops, the numerators, and multiply the bottoms, the denominators. Tray times frac is just frac trap.
Simple enough, but
Yeah.
addition, that's where you hit that common denominator thing.
Right. And that's essential. You have to find a common denominator. You need to rewrite the fractions so they share the same base, the same unit size, before you can add them. Frac meta plus frac becomes frac track. Trayeki.
You're adding like with like?
Precisely. These aren't just arbitrary rules. They ensure we're combining things in a meaningful way.
Yeah.
And yeah, these are the absolute basics everything else is built on. So once we've sort of nailed down those operations with rational numbers fractions, we pretty quickly run into irrational numbers, often showing up as roots or surds, as the materials call them.
Yeah, numbers you can't write down as a neat fraction. Like square 82, they go on forever.
Exactly. And the first thing you need to do is simplify them, if you can.
Right, like the example squirt 12 plus squirt. You don't just leave it like that.
No. You look for perfect square factors inside the roots. Score 2 is a score 12, the 10's $3, which is 2 squirter, and score 2 is score 23, so $3 score.
Ah, so then you have $2 squirt plus 3 squirt. They're like terms now.
Exactly. Now you can combine them easily.
Yeah.
$5 square 3. It's about making things manageable.
Okay, that makes sense.
Yeah.
But then we get to this thing called rationalizing the denominator. The whole point is getting the surd, the root, off the bottom of the fraction. Why? Why do we care if it's on the bottom?
That's a really good question. It's mainly for computational stability and, historically, ease of calculation before calculators were common.
Stability, how so?
Well, dividing by an irrational number, especially one you have to approximate, can introduce errors, or let's say numerical noise, in complex calculations. Think about computer simulations or complex engineering models. Having a clean integer in the denominator is just safer, more reliable. So if you have something like frac score, you multiply the top and bottom by square root.
Right, so you get frac squarty, which is frac squarty. The denominator is rational now, a clean 5.
Precisely. It standardizes the form and makes subsequent calculations more robust.
Ah.
It seems like a small thing, but in complex systems, these details matter.
Here's where it gets really interesting, right? Because now we need to shift scale massively. We need exponents, powers, indices, whatever you call them, to handle the incredibly huge or incredibly tiny numbers you see all the time in science and engineering.
Absolutely.
Yeah.
And this is where scientific notation just becomes indispensable. You can't really operate without it.
It's that mantissa exponent form, right?
Exactly. It's the only sane way to write down and compare numbers like, say, 1 billion, that's $1 times 199, or something minuscule like the charge of an electron.
Which is what, 1.6 over 2 times $1019? Tiny.
Vanishingly small. Imagine writing that out with all the zeros.
Hmm.
Scientific notation makes it compact, clear, and standardized. Much harder to make mistakes.
And underlying all this notation are the laws of indices. The basic one being, when you multiply terms with the same base, you just add the powers. 1 times an AM plus an 8.
Yeah, and that simple rule is incredibly powerful because it actually dictates how the other rules must work. It shows the internal logic.
How do you mean?
Well, for that multiplication rule to hold true universally, it forces other conclusions. Take a 2 LLs times 1 by the rule, that should be a 2 LLs plus a NAM1, which is just a dol.
Okay.
But a 2L1 is also like a 2L main down. So it always a qual is also a dollar. For consistency, a non must mean Franza 1. It's not just a definition, it's a requirement of the system.
Ah, I see. The rules have to fit together. And what about $2? That always felt a bit arbitrary, like we just decided it equals 1.
Not arbitrary at all. That's another consequence. Think about $8 times the 1, 1. By the index law, that's $1 plus $8.
No.
But $8 times a 1 is also a times fracco, which is just fractoid, and anything divided by itself is 1, as long as it's at 0.
So $2 must equal 1 for the rules to be consistent. Wow.
Exactly, and the same logic extends to fractional powers. A 12 has to be squared because a12 times a12 plus 12 a1, the only thing that multiplies by itself to give a day is its square root. And more generally, a nay is the 9th root of a.
It all hangs together. Now, this ties into engineering form, doesn't it? Where the index has to be a multiple of 3.
Yes, precisely. It's a practical application of scientific notation tailored for engineering units. It keeps the exponent as a multiple of 3, like 103 lyres, 106, 199, or $10, 10.6, 10.9, and so on.
Which lines up perfectly with the SI prefixes we use constantly. Kilo is 103 3Is, mega 166, giga $109. And going small. Milli $10, micro 10.6, nano $10, pico $10, even femto $10-15, like femtoseconds.
Exactly. It creates a standardized way to talk about scale using familiar prefixes. It avoids weird exponents like 144 or 10 to ns in final reported values. You adjust the mantissa instead.
Makes communication clearer.
Massively. And it lets engineers shift between scales really easily. Look at the source example, light travel. In 1 nanosecond, 10 to the seconds, light travels about 30 centimeters.
Okay.
In 1 year, it travels $9.46 times 1012 kilometers. That's $9.46 times 1015 meters. The range is immense. Only this kind of exponential index-based language, standardized with things like engineering form, can really bridge that gap effectively, from femtoseconds to light years.
Okay, so let's zoom in on one very specific, very special exponential function. The one using Euler's constant, AG dollars.
It's truly fundamental in physics, engineering, finance, biology, everywhere, really.
It's one of those weird irrational numbers, right? Like pi. Goes on forever. About 2.718.
It is irrational, yes. But unlike pi, which comes from geometry, the ratio of a circle's circumference to its diameter isn't defined by shape. It's defined by growth, by the process of continuous change.
Continuous change?
Yeah, is the natural base for any process where the rate of change is directly proportional to the amount you currently have. Think compound interest calculated continuously, or population growth without limits, or radioactive decay. It just pops up naturally in those situations.
So when we look at the function Euler's exactly, what are we actually describing?
You're describing accelerating growth. As $6 increases, doesn't just increase, it increases faster and faster. It rockets off towards infinity. That's your classic exponential growth curve.
And it's always positive, right?
Yeah.
The dollar never dips below 0.
Never. And importantly, when $6 is an 8, $t is 1, just like any other base raised to the power of 0. That's our starting point often.
But it also describes the opposite, decay.
Absolutely. That's the beauty of Gnosa. The negative exponent flips the behavior.
Yeah.
As increase increases, maybe representing time or distance, the value of any Gnosa gets closer and closer to zero. Rapid decay towards nothing.
And these aren't just abstract curves. The source materials show them modeling real things.
Oh, constantly. They give the example of current flowing through a diode, an electronic component. The relationship might be something like $1 Gauss VV, $1. That exponential term dominates the behavior.
Where dollars is current, dollars is voltage, and Sephora's is some constant.
Right. And you see it in chemical reactions, too. The materials detail an experiment on hydrogen peroxide decomposition. Its concentration over time, NME peak RA4 equals a 20 Becquerel. Eminios is the starting amount, dollars is a decay constant.
And because they understand the properties of nu, they could use the experimental data to figure out dollars and then calculate the half-life.
Exactly. They found it was about 25.03 hours under their test conditions. That predictive power comes directly from understanding Wechsler and the exponential function. It's the natural language for describing these dynamic processes.
Okay, so if exponentials, especially with Basel, describe growth and decay, then logarithms must be the way to sort of undo that, to work backwards.
That's a great way to put it. Logarithms are the inverse function of exponentials. They essentially unlock the exponent.
So the definition, how does that work again?
It's simple, but really powerful. If you have a number dollars expressed as a base raised to some power, sextuple, so $1 sextuple, then the logarithm is defined as logarithm is the power. Exactly. The logarithm asks the question, what power do I need to raise the base to in order to get the number? The answer is the logarithm.
So the example they give, $16 equals 2 under $4.
Right. So the logarithm of 16 to the base 2, written logarithm 16 times $10, must be 4, because 4 is the power you need.
Okay, that clicks. Now, the sources also point out some key things about how logarithms behave, like boundaries.
Yes. Very important. The argument, the number you're taking the logarithm of, the dollar or $6 in our examples, it must always be positive.
You can't take the log of 0 or a negative number.
Nope. Think about it.
Yeah.
Can you raise a positive base, ADAGND, to any real power and get 0 or a negative number? No. AGND is always positive for real. 6, 88 gets positive. So the input to the logarithm has to be positive.
Got it. And what about the log of 1?
The logarithm of 1 is always 0 no matter what the base is, as long as the base is valid, positive, and not 1. Because $2 is under 1. So 1 of the 1 equals 1.
And as the input $6 gets really close to 0...
Then the logarithm heads off towards negative infinity.
Right. But the real practical power comes from the laws of logarithms, doesn't it? For simplifying things.
Oh, absolutely. They mirror the laws of indices.
Yeah.
Adding logs with the same base means you multiply their arguments, like ln 10, using L as for base.
Subtracting logs means you divide the arguments.
Yeah.
To a logger on x, and a multiplier out front becomes a power inside. MK, M and X.
So you could take something messy like the log of x and collapse it. Yep. Combine the first two using addition. Log 10 log time, 3x as usual. Then handle the subtraction in the multiplier.
Yeah.
Log time, one single log term. Much simpler.
That's a huge simplification.
It really is. And we connect this to the bigger picture. That simplification is why logarithms are indispensable tools for engineers and scientists.
How so?
Because they allow us to linearize problems that are fundamentally exponential. Imagine you have data that follows an exponential curve, line tan, ln, lclon, that's curved, harder to analyze.
Okay.
But if you take the natural logarithm, ln of both sides, you get ln.
Okay.
Using the log laws, that becomes ln y plus ln x.
And ln x, just the sex, right? Because log base undoes to the power of something.
Precisely. So you end up with ln a plus kxx. Now, if you think of nln as your new vertical axis variable and $6 as your horizontal axis variable, this is the equation of a straight line. $C plus nln, where ln a, the intercept, and ln is the slope.
Wow. So you turned a curve into a straight line just by taking logs.
Exactly. And analyzing straight lines, that's easy. We know how to do that very well. Find the slope, find the intercept. Logarithms transform complex exponential relationships into simple linear ones, making analysis, prediction, and design so much easier. Hashtag tag outro.
So we've covered quite a journey there, from the absolute bedrock integrity of basic arithmetic,
The distributive rule, fractions.
through handling irrational numbers, scaling up and down with exponents and notation, understanding the unique role of Abelard,
Constant of natural change.
and finally using logarithms to unlock the power and linearize those complex relationships. So what does this all mean when you put it all together?
It means that really every single engineering calculation you can think of, whether it's working out stress in a bridge girder, designing an amplifier circuit, predicting chemical decay rates, figuring out fluid pressure,
Mm.
it all relies completely on having absolute confidence in these foundational mathematical rules.
The whole structure depends on the base being solid.
Absolutely. The fact that the distributive rule works for negative numbers, that fraction addition requires a common denominator, that ED1 is $1,
Mm-hmm.
that's the stuff that gives us the confidence to then use the more complex models involving d-dollars and logarithms for real-world problems.
Mm.
Understanding these foundations isn't just academic, it's the essential prerequisite for understanding any technical field.
Okay, so here's something to leave our listeners with. We've established that dA seems to be this universal constant linked to continuous growth and decay, and logarithms are the tool we use to find the hidden exponent, the power governing that change.
Right.
So think about that general exponential function, maybe a Ilaki or something similar. If dA represents this fundamental rate of natural change, how many phenomena out there in the world, processes we observe every day, are just waiting for us to find the right combination, the right base, maybe the right multiplier dollars, the right starting value with world, to describe them perfectly using this fundamental language of change? Are they all just exponential relationships in disguise?